Yes, sir.
All right. We want to start a new discussion today, and this discussion involves periodic waveforms. What do you think a periodic waveform is? Nobody has a guess? Uh, You've been using a periodic waveform without knowing it. Okay. You've used a waveform that has a period. So doesn't that tell you that it's a periodic waveform? Give me an example of a periodic waveform.
A sine wave.
Yeah, it's a sine wave. A sine wave. Why do you think it's called a periodic waveform?
I think because like each cycle doesn't change, like the waveform stays the same.
Yes, yes. The waveform repeats itself every period. The waveform repeats itself every period. Give me another example of a periodic waveform.
Step signal.
No, step signal is clearly not a periodic waveform. It doesn't repeat itself. Does the step signal repeat itself? No, it's 0 and then it's 1. How is that repeating itself?
The cosine wave.
Say again?
Cosine waveform.
All right, sinusoidal waveform. A sinusoidal waveform is periodic. All right. That's all y'all know? Y'all don't know any other periodic waveforms?
What about a sawtooth waveform or something like that?
What about exactly? A sawtooth waveform repeats itself. Let me stop sharing and let me share all. Okay. Oh, you see my writing pad now?
Yes, sir.
All right. So
The God, right?
Yes.
You know the signals you could get from U of T, like, okay, say if you have 4 U of T, then you go -2, and then you go up again. That thing which you create, like with the box looking, do you know the box looking signal?
That will create, you can create a periodic waveform by using many step functions.
Right, okay, yeah, that's what I'm trying.
But that's only over a short period of time.
Okay, all right.
But that you could create from many step functions. But that's not what I was looking for.
Okay.
All right. So this is sawtooth. What about this one? What about this one? What's this one called?
I'll assume it's a triangular waveform.
Yes, because it looks like a triangle. Triangle. So this is triangular. What's this one called? What's that one called?
That's the one I was meaning.
That's a square waveform, no?
This is square wave.
Right.
It's a square wave, but you don't create this from, you could create this from any steps over a short period of time.
Right, that's what I was thinking in my head, though, when I said that.
But how many, you will need an infinite number of step functions to create this. An infinite number.
Right.
Okay. Now,
What's this
There is
to the top of triangular? The word for the first waveform.
sawtooth.
Okay.
You ever look at a saw?
Right. Yeah.
The teeth look like this. Teeth on a saw. That's why they call it a sawtooth.
Right.
All right, square wave. No. How would you create a square wave with the knowledge that you have? Well, maybe you don't have this knowledge. You know there's a function called, okay, you know of u of t, you know that function. Well, there's a function called sine of t. There's a function called sine of t or sine of x. So let's go with sine of x. What do you think sine of x is equal to? Well, u of x is equal to what? What is u of x equal to? It's equal to 1 for x greater than 0. Equals 0 for x less than 0. What does sine sound like? What does sine sound like? Sine of x. Sine of x means you don't care about the value of x, you only care whether it's positive or negative. So sine of x equals 1 for x greater than 0 equals negative 1 for x less than 0. So it's very similar to u of x. Okay. Sine of x is very similar to u of x, except that for x negative, u of x is 0, whereas sine x is negative 1. Okay. What's the magnitude of x equal to? What's the magnitude of x equal to?
What you want this for again? The square one?
No, I am defining two new functions. I will get back to the square wave. I am taking a tangent right now. You all know what the absolute value of x is equal to?
X.
What's the magnitude of 1? What's the magnitude of negative 1?
1.
All right. So it's the value of x disregarded its sign, right?
Yes, sir.
So it is just the value of x without the sign. It is equal to x if x is positive. It's equal to negative x if x is negative. Okay. So the absolute value of x, the magnitude of x, just looks at its size. It's 1, it's 1. Disregards the sign. Sine of x just looks at its sign. This is positive 1, and this is negative 1. So sine of 1 would be 1. Sine of negative 1 would be negative 1. Sine of 2 would be 2. Sine of negative 2 would be negative 1. Because you just look at the sign. So x then is actually the magnitude of x times the sine of x. That's what x is equal to. This part gives you the sine, and this part gives you how big it is. Anyway, the thing we're interested in right now is if you take a sine wave and put it through a sine.
I gotta go put that back 1 second, please. All right.
If you take sine wave, if you take sine wave and you put it through a function, sine of x, what happens? What do you have on the output? What do you have on the output? Well, for the first half cycle, that's positive, isn't it? So you have positive 1. On the second half cycle, it's negative, so you have negative 1. And then it just keeps on going. This part here, the input's positive, therefore the output is positive 1. This part here is negative, therefore the output is negative 1. So what have we done then? What have we done? We changed the sine wave to a square wave. That's what we've done. All right. So if you want to create a square wave, you want to create a square wave in PSpice, all you have to do is generate a sine wave and put it through a block diagram called sine of x. And on the output, you'll have a square wave. And I show you that in figure 2 of the document that I sent you.
Oh, the Godred.
Yes.
What a square wave could do, what a sine wave can do. Like, why would you need a square wave? Like in real life?
I got very limited time today. I'm going to have to stop at 11 o'clock. But there are reasons why you would need a square wave.
I have a question. The last thing you wrote with the arrow, what word is that?
With the arrow. You mean up here?
Leave. No, so right at the bottom. By your finger. Leave. I think leave is the apparent leave.
Square wave?
Yeah.
Square wave?
Oh, all right. Yeah.
I'm just repeating what I had up here.
I can understand that. Thank you.
All right. We can see right now how a square wave differs from a sine wave. We can see right now. Okay. So let me get back to what Mr. Fourier says. Mr. Fourier says, if you talk about a sawtooth, you talk about a triangular, you talk about a square wave, you talk about any periodic function, then that function consists of an infinite number of sine waves. Seems strange to you, doesn't it? This square wave has an infinite number of sine waves in it. An infinite number. So when you want to create a waveform that has lots of sine waves, you could create a square wave. Now, the handout I sent you, let's look at that now, demonstrates this. This figure 1 demonstrates this. Okay. I'm saying when you add all, you see I created what? I created 1, 2, 3, 4, 5. I created 5 sine waves. I created 5 sine waves. And just use these 5 sine waves, you're going to see the more sine waves I use, the closer will I get to a square wave. So bear with me. That's where I'm headed. What is V1 equal to? What is V1 equal to?
V1 equal to 1.273 sine. This is 1,000 G.
No. I don't know why y'all ain't got this straight yet. The difference between F and omega. It's not sine of FT.
Oh,
is sine of omega t. So it's 2000 pi t. It's 2000 pi t. See, that's V1. And by the way, this here is just an approximation for 4 over pi. 4 over pi. Okay, I'm not yet going to tell you where I got that from. Okay. Okay. What's V2 equal to?
Um, 0.4244 times sine open bracket 3000 pi close bracket t pi t close bracket.
It is not multiplied by pi. It is multiplied by 2 pi.
6,000 pi.
All right? Or 3 times 2000 pi. Okay. And this number here is 4 over 3 pi. And this number here, this brings here is 3 times. We call this the fundamental. We call this fundamental. Or this whole waveform we call the fundamental sine wave. And this will be the fundamental frequency. And the V2 is the third harmonic. It is 3 times the fundamental. It's the third harmonic. It's just language. You just have to learn the language. So you see, I have it there. Fundamental. That's the one with the lowest frequency. Okay. Third harmonic, that means that's 3000. The fifth harmonic, that means it's 5 times the fundamental. The seventh harmonic, 7 times the fundamental. The ninth harmonic, that is 9 times the fundamental. Okay. Notice we are only using odd harmonics. We are only using odd harmonics because I'm trying to create a square wave here, although you don't know that yet. And how many harmonics you have? You have an infinite number. And I chose to stop at the ninth harmonic. Not only that, what's the amplitude? What is the amplitude? The amplitude 4 over pi. This is 4 over pi. This is a third of that. A third corresponds to the third harmonic. A fifth corresponds to the fifth harmonic. A seventh corresponds to the seventh harmonic. And the ninth corresponds to the ninth harmonic. So, let us back up now. What's VB equal to? What's VB equal to?
That would be the voltage between the third and the fifth harmonic.
Young man, I don't know what that means. I don't know what you just said. What do you mean by the voltage between? What does that mean? Voltage is always across. Voltage is never between. Voltage is cross. Where is VB? Where are the 2 points VB is across?
VB is across V3, V3, and V2.
Absolutely not. Absolutely not. See, y'all still don't know how to read piece-by diagrams. You still don't know how to read them. VB is from this point. VB is from this point to ground. You only name one point. Where's the other point? It's always ground. You should have learned this as 110. If only one point in the diagram is identified, then where's the other point? Ground. VB is from here to ground. What is VB equal to? Say again, please. Yes, V1 plus V2. And KVL tells you that. Even if you can't figure out these two are in series. VB is V1 plus V2. Okay? So, VB is V1 plus V2, which is 4 pi sine of 2000 pi t plus 4 over 3 pi sine 3 times 2000 pi t. That's VB. Or VB equals 4 over pi, the sum of n, 1 over n sine n 2000 pi t, where n equals 1, 3, 1 to 3, 1 to 3, and odd. That means skip out 2, 4, whatever. So that's what VB is equal to. That's VB. Don't you agree that this here is just shorthand notation for this? Now, let's go back. Let's go back. What's VC equal to? What's VC equal to? Yes. Okay. So VC equals, well, I could just make a shorthand, VB plus V3. Okay. So that is, well, let me go ahead and write V1 plus V2 plus V3. Okay. And let me write it out again. 4 over pi sine 2000 pi t. Okay. Plus 4 over 3 pi sine 3 times 2000 pi t plus 4 over 5 pi sine sine 5 times 2000 pi t. Okay. And again, how do we write that succinctly? How do we write that succinctly? Again, that is 4 over pi sum n equals 1. The 5, and again, n odd, of 1 over n sine n 2000 pi t. Okay. And then Mr. Fourier says, well, let's see what's happening. Okay. So VA is just a single sine wave. VB is the sum of the fundamental plus the third harmonic. VC is a fundamental plus a third harmonic plus a fifth harmonic. Okay. So as the number increases, we should start looking more and more like a sine wave. And here you have it. Like a square wave, sorry. Here you have it. Okay. What's the green? The green is VA. You see down there, VA? That's a single sine wave. Okay. And then VB is a red light thing. And you see that's closer to a square wave. Okay. And then VC is a blue. And the blue is even more closer to a square wave. Okay. And when we take an infinite number of these, we will have a square wave. Okay. This demonstrates you could create a square wave by using the right sine waves. The right sine waves.
How much would you need for it to be very, very close to a square wave?
That depends how you define very, very close. Look at the last one. That's up to the ninth harmonic. Okay. So the very last one, I don't know what color that is. It looks like purple to me. Okay. That looks more and more like a square wave of amplitude 1. Okay. Now the truth of the matter is, I kind of simplify the truth a little bit here. The truth of the matter is, it never quite looks like a square wave. A square wave does this. Okay, if you take an infinite number, it'll look like this. You'll see the ripple. Okay. And this is what Mr. Fourier says. Mr. Fourier says a square wave. This is an odd square wave. Okay. What makes a function odd? What makes a function odd? This square wave here that we generated is an odd function. What makes a function odd?
Uneven values.
Like if the amplitude start.
Folks, listen to me. You all have Mathematics 7 and Mathematics 8. I'm sure you all at one point talked about even and odd functions. What was the definition of an odd function?
It has symmetry on the graph.
What kind of symmetry?
On the y-axis.
And what? Yes, but tell me what are you looking for?
Right.
If you hold a mirror on the y-axis, what you see on one side of the mirror is the negative of what you see on the other side of the mirror. That creates an odd function. Or mathematically, it is f of negative x is equal to negative f of x. That's a mathematical definition. In practice, you can recognize it by holding a mirror here. If this side of the mirror is the negative of that side of the mirror, then you have an odd function. An even function on the other hand, this is this is an odd square wave. And this is an even square wave. Okay. Why? You hold the mirror at the y-axis. What you see on this side is just a reflection of this side. Or another way of saying the same thing. Another way of saying the same thing: f of x, f of negative x equals f of x. Give me another example of an even function. Give me another example of an even function.
Will that be a cosine?
Yes, a cosine. There you go.
Cosine.
No, cosine. Cosine. Not sine. Sine is up here. This is sine. This is sine. Sine is odd. A sine wave is odd.
Oh, okay.
Okay, this is cosine, which is also even. Okay.
Dr. Godwin.
Yes, go ahead.
So that means you can make a function or a wave odd or even by simply shifting it?
Absolutely. That's absolutely correct. Okay. So let's get back to the odd. We were actually what we generated just now. What we generated just now was an odd square wave. Okay, that's what we generated. Okay. And there we saw, okay, Mr. Fourier says that V square wave equals 4 over pi sum of n equals 1 to infinity of 1 over n sine n times the fundamental frequency times omega 1 t. Okay. This here is called the Fourier series. The Fourier series. Okay. And let me go back a minute. This coefficient here is called B1. That coefficient is called B1. This coefficient is called B3. So this is B1. Why? It's coefficient of a sine wave. That's the fundamental, because we have 1 times here. This is called B3. That's a coefficient of the third harmonic. Okay. B3 corresponds. B, because it's multiplying sine. 3, because the harmonic is the third. And this one would be B5. Okay. So let me rewrite this then. Let me rewrite this final statement. V square wave is 4 over pi times sum, and I gotta say here, n odd. Sum of n equals 1 to infinity. Make sure n odd of what? 1 over n. Or in this case, bn. I need more space.
I didn't get a screenshot of the last thing. Oh, I see you mark it out. Never mind.
So, in general then, so V square wave is equal to 4 over pi. I'm just rewriting what I had on the previous page. Sum of n equals 1 to infinity of B n sine and omega 1 t. Okay. Where Bn is 1 over n. Because that's what we showed earlier. V square wave odd, I should say, is equal to that. I'm not going to prove it to you, but I'm just going to state it. V square wave even is equal to 4 over pi, sum of n equals 1 and odd, to infinity and odd of a of n cosine. An even function has to consist of even. You make up an even function by adding even functions. So this has to be cosine on sine and omega 1t. Where a of n now is actually negative 1 to the power of n. I think it's the other way. I think it's negative 1 to the power of n over n. In other words, these alternate. So in other words, this here is equal to 4 over pi cosine omega 1t minus minus 1 over 3 cosine 3 omega 1t plus 1/5 cosine 5 omega 1t, all the way up to infinity. Okay. So the magnitude of coefficients are the same. The magnitude are the same as the odd square wave. But the signs are not the same. The signs alternate. Okay. Now, that's a square wave. Mr. Fourier says this. Any waveform is equal to any periodic waveform. Any periodic waveform. And that periodic waveform can be odd or even or neither. Any periodic waveform equals A0 plus A1 cosine omega 1t plus B1 sine omega 1t plus A2. The square wave didn't have any even functions, but you could get waveforms with even functions. Cosine 2 omega 1t plus B2 sine 2 omega 1t. And don't forget, omega 1 is the fundamental. And that's 2 pi over the period. That's 2 pi over the period of the periodic waveform. This is for the periodic waveform. Plus A3 cosine 3 omega 1t plus B3 sine 3 omega 1t all the way up to infinity. And we write that succinctly as A0 plus sum of n equals 1 to infinity of A of n cosine n omega 1t plus sum of B of n sine and omega 1t. That's what Mr. Fourier says. Okay. I bet you all never suspected this. I bet you all never.
Jade,
Yeah, go ahead.
which question on the final exam is information pertaining to?
The very last one.
Very last one. All right.
It amazes me that students want to learn not for the knowledge of technology, but for what's on the final exam. That just blows me away.
I mean, you got some people who do their job not because they love their job, but because they need the money, for rent and the live
No,
life.
man, listen to me. I don't know if you remember, but last class I was talking about the fact that I used to work in the industry. And I rather teach. Teaching pays less money than working in the industry. Yet I decided to work in the industry because what do you do most of your adult life? You work. So if you're not enjoying your work, you're hating most of your life. It's far more to get satisfaction from your work because you'll have a better lived life. So the person who finds a job that he really likes and pays reasonably well, he can make a living off of it. That's a happy person. A person who hates his job every day is the people who give you trouble at that job in any field. The people at their jobs in any field, name the field, and there's some people there who shouldn't be there because they hate what they're doing.
That's majority of people on the job.
Well, I hope that's not true. I hope that's not true because they have sucky lives then.
I saw
Anyway,
in the
reality,
Bahamas,
man.
that's true though. Like
Excuse me?
especially in the Bahamas, like majority of people don't like their job.
Well, that has not been my experience, but that doesn't mean it's not true. But let me tell you, at any job, there's somebody who came at the bottom of the class. So when you choose a doctor, keep that in mind. There's a doctor you may be going to who is very lousy in his classes. And he doesn't know what he should know. All right. Let's relate this. Let's go to the final. Let's relate this to the last question on the final exam. Let's relate what we did so far. By the way, A0, you already know what A0 is. Anybody want to guess what A0 is? A0 is just a constant. That's the average value of f of t. A0 is the average value of f of t. So A0 is going to be what? A0 is going to be 1 over period, integrate over a period of f of t dt. All right. And we already know how to do this. I'll tell you hope before this lesson's over how we get A1 and A2 and A3 and A4. I mean, how did I know to pick 4 over pi and 4 over 3 pi and 4 over 5 pi? How did I know what coefficients to use when I did that simulation? because there's a formula to get those. And very quickly, let me give you that formula very quickly in case I forget. A of n is 2 over the period. 2 over the period. 0 integrate over the period, not of f of t, but f of t times cosine and omega 1 t dt. So if you want A1, just put 1 here. Similarly, B of n is 2 over the period, 0 integrate over period, f of t sine and omega 1 t dt. Okay, I'm just giving you these formula. I'm not telling you where they came from because I don't have time to. Bn and an and a0 together they call the Fourier coefficients. The Fourier coefficients.
Oh, the guy, right?
Yes.
You plan on walking us through the last question this class?
No, I'm not planning on solving that equation. I'm planning on just telling you how that question relates to what we've been doing. I'm not planning on solving it for you.
A question like this coming on the final then?
I'm not going to tell you that. See, if I tell you no, you ain't gonna study this stuff. But this stuff is important. You're gonna need this in foreign class in the classes that follow.
I know, but
study it during the
learning it
break.
in a short period of time and to say
Excuse
study
me?
this without you, like you, this you just teach us in such a short period of time.
So what? I keep telling you must study after every class. I've been telling you that all semester.
Yeah, Dr. Cartwright, but when I go home and study this, that don't mean I can get 100%. I ain't got an opportunity to come back and ask you no more questions after the day.
You have a question, email me.
All right.
I don't know why students think that the last day of class can't be on the final. That boggles my mind, especially since I tell you must study after every class.
Don't worry, Dr. Cartwright, we can be prepared to this final.
Yo, man, I don't want to hear bullshit like that. I just want don't tell me that nonsense. Show me.
Oh, yeah, nonsense.
Show me on Friday. Show me on Friday.
Assure you.
Yo, man, I'm saying to you, I don't need that kind of reassurance because it doesn't mean anything to me. What you say, it doesn't mean anything to me. What you do means something to me. So show me. All right. Let's look at where's the final from last year. Give me a second here. Let me see if I can find it. I think that's it. Hopefully that's it. All right, here we go. See there? 6. A certain periodic band limited signal. What does that mean? What do you think band limited mean?
When I have band, I think like bandwidth. I don't know.
It means we don't have infinite number of signals. We don't have infinite number of sine waves. Okay. So the bandwidth is what? What do you understand by bandwidth? What do you understand by bandwidth?
It cut off at a certain point in time, like the signal stops.
Not time, and frequency.
Oh, okay.
There's a highest frequency and there's a lowest frequency. And the difference between the two is the bandwidth. I mean, you also know that from 243. Now, I'm not using X and T here. Okay. There's N, and it's your number. So let's make N1. Okay. So then we have X of T equals 10 cosine 2 pi T plus 20 sine pi T plus 10 sine 6 pi. Excuse me?
I still see in your email. I want to know if you're supposed to be on your notepad.
You see in my email?
Or at least the document, yeah.
You see in my email?
Yeah.
So what is he talking about then?
I hear you working on something. I want to know.
I was working on the pad, but I just put where I see N in question 6, I replace it by 1. Okay, so let's go to that now. All right. Can you identify any of the A's? For example, what is A1? I am asking you to identify this equation with what we wrote for the Fourier series. Well, okay, what's the lowest frequency? What's the lowest frequency? Yo, man, when you see 1,000, are you looking at my pad? Why are you talking about the other thing? Are you talking about question 6?
The lowest frequency is 2.
Don't talk fool, young man.
And the widths.
How is it y'all can't identify frequency yet?
The lowest frequency is 1. Is it 2 pi?
1 what? 1 what?
1 hertz.
1 hertz. All right. So this is 1 hertz. This is 1 hertz. And what's this one?
That's 3 hertz.
That's 3 hertz. Okay. So these two are what? What are those two? That's the fundamental. Those are the fundamental sine waves. This is the fundamental frequency. And what is this one?
The third one.
Yeah, and what do we call the third one?
You mean third harmonic times the fundamental?
The third, not the third harmonic. We call this the third harmonic. Okay, that's the third harmonic. All right. Knowing that this is the fundamental, what coefficient is this? What do we call that coefficient? We call that coefficient A1. What do we call this coefficient?
B1.
B1. What do we call this coefficient? Excuse me? What do we call this coefficient?
I assume P2.
Let's go back to the previous page. Because clearly, this went right over your all heads. What is A1? A1 is a coefficient of the cosine fundamental. B1 is a coefficient of the sine fundamental. A2 is a coefficient of the second harmonic cosine term. B2 is a coefficient of the sine second harmonic. A3 is a coefficient of the third harmonic cosine. B3 is a coefficient of the third harmonic sine. Do you see the process?
Yes, sir.
Now let's apply it to this problem.
So
This is the
B3.
fundamental cosine. So that's so it's B3. Thank you very much. It's B3. Okay. So when you see any periodic waveform, yes, this is periodic. This is a periodic waveform. What's the average value of this waveform? What is A0? What is A0?
Could I see the previous page to look at the formula?
Yeah, man, you don't need to look at the form, but anyway, let's go. Let's see if that helps you any. What's A0? Really? Nobody can tell me what A0 is?
If I had to guess, would that be 10?
Why would you think it's 10? Why would you think it's 10, Mr. Buchap?
I was just guessing.
No, but why did you guess that?
Because that's what's in front of the waves, like the cosine and
But didn't we call that A1?
yeah.
What was A0? In this equation, what was A0? A0 is just a number. A0 is just a number multiplying nothing. A0. Where do you see just a number not being multiplied by anything? It's not there, therefore it is 0. A0, 0, why? If this had been +6, if this had been +6, then A0 would have been 6. Doesn't that make sense? And not only that, how else you know A0 is 0? Because the average of x is the average of this cosine, the average of sine, and the average of sine. The average of any sinusoid is 0. The average of that is 0, the average of that is 0, the average of that is 0. All right, so right off the bat, we know that there's no DC term in x of t, because the average value is the DC value. All right. What am I asking now? What's the question asking? All right, 2. What is the fundamental frequency? Well, we already established that. The fundamental frequency is 1 hertz. What is the average value? I just asked you that. 0. The part you can't do is part 4. Part 1 you could do. All they're asking you in part 1 is you have a cosine wave of 1 hertz. You have a sine wave of 1 hertz. Add them together. So you get 1 magnitude. You get 1 magnitude A and 1 magnitude theta. One phase theta. We've done that in this class numerous times. So right now, the only thing you can't do in question 6 is part 4, which we don't have time, unfortunately, to do. But which I will do. Remind me to do this in 410. Remind me to begin 410 with part 4. Because
That means you can't put down the final exam because you didn't show us.
young man, I am not going to give you a question on the final exam I have not taught you.
All right then.
Okay.
Well, I got you
I
mentioned
don't need-
on the last page before you leave. Just saying.
Okay, I really gotta leave. Give me a second, please. All right. There's the last page, Mr. Pintoy.
All right, thanks.
All right.
And that was for question 1, right?
Excuse me?
Question 1 of that was for question 1 of question 6.
What do you? What? What do you, I don't understand what you're asking.
No,
That was just this. That was this. Right, that's a single sine wave
all right. Thanks.
because they got the same frequency, but one's cosine, one's sine. So that adds up to being one single frequency with a different amplitude, an amplitude between an amplitude that is not 10 and not 20, and a phase. That sine wave will have a phase. Yeah. Folks, anything else? Because I got a 12 o'clock exam on campus.
We should.
Good luck to you on Friday. But if all of you had worked hard every day, you wouldn't need any luck.
Oh man, I can use all the luck I could get.
Yeah, I know, because you didn't work every day. Anyway,
Oh,
see you all later. See you on Friday.